Welcome back to Statistics. I'm Dr. Jeff Groh. Today we're going to talk about hypothesis testing. In many ways, this has been the goal of the course all along. The definition is quite long and will take some time to explain. A hypothesis test has a null hypothesis denoted by H0, and it specifies the value of a parameter. So, for example, you may have mu equals some number. We'll call it mu0. Typical thing might be mu equals 52.0. Might be an example. Mu0 is just some number that you're going to use to specify the value of, say, in this case, the parameter of the mean. So every hypothesis test has a null hypothesis, but it must also have an alternative hypothesis. The alternative hypothesis is denoted by H with a capital A as a subscript. There are three forms. Let me give you some examples. The alternative hypothesis might be that the mean is not the specified value, or that the mean is strictly greater than the specified value. And only one other option, the mean is less than the specified value. So the alternative hypothesis will have one of these three forms. When we say that mu is not mu0, this is a two-tailed test. We assume it's here, but if we end up either here or over here, we'll assume that it is not. The other two options are one-tailed tests. If mu is assumed to be greater than mu0, this is a right-tailed test. We're assuming the mean is here at mu0, but if we get a value that's too far to the right, somewhere way over here, for our sample mean, we'll conclude that it is probable that the mean is in fact greater than the specified value. The alternative hypothesis that the mean is less than mu0 is a left-tailed test. We'll have some specified mean mu0, but if our sample mean ends up way out here in the left tail, we'll conclude that it is probable that the population mean is in fact less than the specified value. There are two possible conclusions. One, we reject the null hypothesis. Two, we fail to reject the null hypothesis. In no case do we say that the null hypothesis is confirmed or that it's true truth is not part of what we're doing here. Everything we do in statistics is about probabilities, not about truth. And so it's about confidence more than it is about belief. How confident are we in our conclusions? If the mean is proposed to be at some point x naught, mu naught, but we get a sample mean that's way out here in the tail, it's unlikely that the mean is mu naught. And so we might reject the null hypothesis. We're not saying the null hypothesis is false. It might still be true. It might be a fluke that our sample mean was way out here in a tail. However, our confidence in that null hypothesis has been diminished. And so we will reject the null hypothesis. That doesn't mean that we're saying the alternative hypothesis is true, however. We don't say things about truth here. If we get a mean over here close to the hypothesized mean, that doesn't mean we're saying the null hypothesis is true. It's just that we fail to reject the null hypothesis. We're not assuming then that the alternative hypothesis is false. That's not what we do at all. We don't have confidence to change to the alternative hypothesis. There are two methods for drawing a conclusion for a hypothesis test. One is the p-value method, and two is the critical value method. With either method, we must first specify a level of significance called alpha. Alpha is going to be the area in the tail. We have, to this point in the course, chosen alpha to be at, say, 5%. If something has a probability of less than 5%, we call it unusual. So let me show you how these two methods will work once you've specified alpha. Here's your null hypothesis mean. For the p-value method, you'll take your sample statistic, your mean, and calculate the area from there on out. If that area is greater than alpha, then you fail to reject the null hypothesis. If the area is less than your level of significance, then you reject the null hypothesis. That area represents the probability of getting the statistic that you found, or further, if the null hypothesis is true. This is for a one-tailed test. For a two-tailed test, you'll take the corresponding area on the other side. So basically, for a two-tailed test, you'll find the probability of getting this far on either side. For a one-tailed test, just the probability of having the statistic that you found on one side. If the null hypothesis is true, we have a distribution of sample means that will be essentially a normal distribution, or something close to a normal distribution, perhaps a t-distribution. The alpha value that we choose is the probability of rejecting the null hypothesis even when the null hypothesis is true. So alpha is the probability of what we call a type 1 error. type 1 error is when you reject the null hypothesis when the null hypothesis is true. We will always have that possibility in statistics and with hypothesis testing. Anytime you take a measurement, that measurement will have the risk of having errors in it. Our sample means may not be representative of the population. There's always going to be the possibility that the sample that we chose was unusual in its own right, out of the ordinary compared to other simple random samples. So we will never have zero probability of error. There's always going to be some possibility that we will reject the null hypothesis, even when it's true. So again, for the p-value method, on a two-tailed test, you take the area from wherever your statistic is out to infinity and double that. Twice that area. This total area, if that is greater than the specified level of significance, then you fail to reject. The null hypothesis, if it's less than your level of significance, then you reject the null hypothesis. For a right-tailed test, you just take the area in the right tail, and if the area is greater than your level of significance, then you fail to reject. If it's less than your level of significance, if it's so far out that this area is smaller than your level of significance, then you reject the null hypothesis. The same kind of thing is true for a left-tailed test. For the critical value method, on a two-tailed test, we find critical values x crit left and x crit right, so that these areas are half the level of significance. If the sample statistic falls in one of these critical regions, then we reject the null hypothesis. The probability of that event will be smaller than the level of significance. If the sample statistic falls here, then we fail to reject. The null hypothesis. For a one-tailed test, there's only one critical value where the area is the entire level of significance alpha. If your sample statistic falls in the critical region, then you reject the null hypothesis, and if it doesn't, then you fail to reject. You'll only reject the null hypothesis if the probability of getting that value, given the null hypothesis is true, is smaller than your level of significance. This is the way science works. You don't necessarily claim that some scientific theory is true. Rather, you have confidence that results will replicate something close to the specified value of a parameter. Only when experiments show that that specified value of the parameter is improbable do you reject the null hypothesis. But even then, you're not saying the null hypothesis is false, just that it's improbable. The alternative hypothesis isn't the assertion of something being true either, only that it's likely that the specified value is not that was proclaimed originally. Let's do an example. An auto manufacturer claims that its new model gets 47 miles per gallon. Let the null hypothesis be that the mean is 47 miles per gallon. So we're going to assume they're true until we can demonstrate otherwise. We have nothing else to go on than their claim. We'll take their claim as the null hypothesis, and we'll do some sample testing to see if it stands up. For our alternative hypothesis, we'll suppose that the mean is in fact smaller than the 47 miles per gallon as the alternative, that they kind of erred on the high side. We'll let our level of significance be 0.05, and this being a left-tailed test, we'll put 5% of the area in the left tail of our distribution. A test of 40 cars. So we've tested 40 cars. The sample size is 40. And this is a large sample as far as we are concerned. It justifies the use of the normal distribution. It's greater than 30. It's greater than 30. And in the test of 40 cars, we have 41 miles per gallon as the average. And our sample standard deviation is 2.5 miles per gallon. What do we conclude? In this case, we're given the sample standard deviation. So we can still use a one-tailed t-test. Though a one-tailed z-test would also work. Our sample mean was 41. The hypothesized mean was 45. Our sample standard deviation was 2.5. What do we conclude? We can use our calculators to do all of the work for us. We're going to press Stat on the calculator and then go over to Tests. We'll scroll down to a t-test. You can either input data in the form of a list or the statistics, which is what we are going to do here. The mu naught is the null hypothesis mean, which in this case is 47. The sample statistic was 41 for the mean. The standard deviation was 2.5 from the sample. Number of elements in the sample was 40. In this case, we're going to choose a left-tailed test, and we'll just have this calculate the value. It gives us a p-value that is essentially 0. That's because the t statistic is 15, negative 15, which means we're 15 standard deviations below the mean. When we say standard deviations here, it's using the standard deviations for the sample's means. That means take the sample standard deviation and divide by the square root of the sample size. That's the standard error for the distribution of sample means. And it tells us that the p-value is essentially 0. It's so small that there really are some other decimals out here, but they're so far out that it rounds it to 0. That's way less than alpha equals 0.05. And so we will reject the null hypothesis. Our data will show that it is improbable that the null hypothesis is true. We're not saying that the manufacturer is lying, just that our data do not support that conclusion. They support the alternative hypothesis. With a p-value that is 0, we can make this claim with a very high level of confidence. We could have done this with a critical value as well. What would the critical value be in this case? We'll have to use x bar equals 41, s equals 2.5, and n equals 40 to figure this out. For a normal distribution with alpha equals 0.05, where is that critical value? We can use the norm inverse. To figure this out using this left tail. The critical value can be found by using inverse normal. So we'll press second and then distribution. We'll scroll down to inverse normal. The area that we've chosen is the level of significance. So that's 0.05. The null hypothesis mean was 47. Standard deviation was 2.5, but the sample size was 40, so we divide that by the square root of 40 to get the standard error for the distribution of sample means. This is a left-tailed test, and so we get a critical value of 46, slightly less than 47, which was the null hypothesis mean. Any sample mean that we get that is less than 46.3 will cause us to reject the null hypothesis. In order to fail to reject the null hypothesis, the sample mean has to be between 46.3 or anything higher. So the about 46.3 or so is the critical value. Our mean was 41. It's in the critical region, and that means that we reject the null hypothesis. The critical thing to do here is finding these critical values using inverse norm, or norm inverse, using a spreadsheet. We have to use the null hypothesis mean, but the standard deviation will be the sample standard deviation divided by the square root of the sample size. It's very important that you use this value. This will give you then the critical value that you have. If your x falls to the left of that in this one-tailed test, then you reject the null hypothesis. I have to tell you that when I was a young lad, I had a car that advertised that it got 40 miles per gallon. But in my experience, having calculated this, it never got much more than 25 miles per gallon on the freeway. So my experience shows that this kind of thing is not unheard of. Consumer Reports claimed that mean braking distance at 60 miles per hour on wet pavement for a certain car was 159 feet. Equipped with new tires, having a fancy tread design, um, 45 cars were then tested. So first, with the standard tires, 60 miles per hour, the mean was 159. We have new tires. We have no reason to believe that they behave any better or differently. So the null hypothesis mean here will be that the mean with the new tires is still 159 feet. The mean on the test of these 45 cars was 148 feet, with a standard deviation of 23.5 feet. Use alpha equals 0.01. We only want a 1% chance of making a type 1 error where we reject the null hypothesis when the null hypothesis is true. Use this to test if these results indicate a reduced stopping distance. We have to decide what the alternative hypothesis is based upon the statement of the problem. In this case, we're testing whether or not the stopping distance has been reduced if it's less than 159 feet. The sample mean was 148, but that is, after all, from a sample with a standard deviation of 23.5 feet. And we've chosen a level of significance of 1%. So this will be a one-tailed test, and we'll use the one-tailed t-test again. So we'll go to Stat, Tests, and then t-test. We'll input the stats as before. This time, the mean is 159 feet. The sample mean was 148 feet. The sample standard deviation was 23.5 feet. And the sample size was 45. The test is a left-tailed test again to see if it's been reduced. And we'll calculate. You can see that the p-value is 0.0015. That's 1/10 of 1%. That's definitely less than 1%. Also note that the t-statistic is negative 3.14. That's more than 3 standard deviations below the mean. That means this is a rare event, and we can see how rare. About 0.15% chance of that happening. So this is a case where we reject the null hypothesis. This p-value tells me everything I need to know. This is less than alpha, which is 0.01%. Therefore, we reject the null hypothesis. Here's another example. Suppose it is advertised that the average trout at a particular lake is 19 inches. There's your null hypothesis. We'll take their claim until we can demonstrate otherwise. 73 fish are caught with the mean size of 18.7 inches and a sample standard deviation of 3.2 inches. Do these indicate that the mean is less than 19 inches? Use alpha equals 0.05, so a 5% level of significance. Our null hypothesis is that the mean is 19 inches, and the alternative hypothesis is a one-tailed test, that the mean is less than 19 inches. We'll use stat, and then go over to the tests, and select the t-test again. In this case, the null hypothesis mean is 19, and the sample mean was 18.7. The standard deviation was 3.2, and sample size was 73. This is again a one-tailed test, and so we'll just calculate the value. Everything we need to know is in the p-value. The p-value is 0.21, which is greater than our level of significance of 0.05, and therefore we fail to reject the null hypothesis. You can see this with the t-value as well, which is only negative 0.8. That's less than 1 standard deviation below the mean, which is not a very rare occurrence. In this case, the p-value that we get is 0.213, which is definitely greater than 0.05. Therefore, we fail to reject the null hypothesis. We do not have sufficient evidence to show that the null hypothesis is not true. Note that belief is a hard word to come by in this business. It's more about confidence. We're not confident enough to reject the null hypothesis. A 5%, well, on a left-tailed test, the 5% level will be here. Our value is here, too close to the mean to reject the null hypothesis, so we fail to reject. We're not saying that the null hypothesis is true, just that our evidence isn't strong enough to counter this claim at all. Hopefully you can see that this is where the rubber meets the road in statistics. This is where we make claims and counterclaims, and we can test these claims. We never talk about the truth or falsity of these claims, only that we can have confidence or lesser confidence in these claims. However, we do have this notion of type 1 error and also type 2 error. Remember that type 1 error is when you reject the null hypothesis when the null hypothesis is true. The type 2 error occurs when we fail to reject the null hypothesis when the null hypothesis is false. So let me explain how this could happen. We have a distribution of means around the population mean. It could so happen that we choose a sample where the mean is so far out in the tail that we reject, even though the distribution really is nice and normal like this. Type 2 error can occur when we have this null hypothesis mean here, but the true mean is over here someplace. And yet, it's still conceivable that we could get a sample mean out here, even though the true mean is way out here to the right. And we could fail to reject the null hypothesis, even though the null hypothesis really is false. For type 2 error, the null hypothesis mean is out here someplace, but the actual mean is over here. With our null hypothesis mean, we're assuming somehow that the distribution looks like this, when in fact it looks like this. We might reject the null hypothesis, given some level over here, but at the same time, the probability of not getting that far out will be beta. So alpha is the probability of type 1 error, beta is the probability of type 2 error. We'll have some critical value beyond which we'll reject the null hypothesis, but if the null hypothesis really is false, this area then will be the probability of failing to reject the null hypothesis when the null hypothesis is false. The power of a test is 1 minus beta, 1 minus the probability of a type 2 error. This is the probability of rejecting the null hypothesis when the null hypothesis is false. That is what the power of a test is. In testing a claim about a proportion, the test statistic will be a z-statistic calculated by the sample proportion minus the null hypothesis proportion divided by the square root of PQ divided by N. You'll recall this is the standard error in the case of sample proportions. And we will use the normal approximation to the binomial distribution, but, and a big but, without the continuity correction for big samples. For example, an oil company claims that 22% of all car buyers use brand A gas. Test this claim with a level of significance of 0.01 if a random check shows 58 of 200 cars use brand A gas. We need to determine what kind of test to use. Our null hypothesis will be that the proportion is what they claim, 0.22. Critically, the alternative hypothesis doesn't say more or less, only we're going to check and see if it's different. Since we use z-scores, the distribution will be a standard normal. For the standard normal distribution, there are critical z-scores that you can find in a table. The critical z-scores will have to divide that 1% in each tail. Here's the null hypothesis mean, and we're going to have to split that alpha over 2 in each of these two tails. So 0.5% in each tail. The critical z you can find with an inverse normal, or you can look it up in a table. We'll use second distribution and then inverse normal. The area is 0.005. We'll use the standard normal curve and we'll select a right tail. And that gives us the critical z-score of 2.576. And that gives us 2.576. Because of the symmetry of the standard normal distribution, the other one will be at negative 2.576. The way this test will work is if the test statistic that we get is in the critical region bigger than 2.576 or smaller than negative 2.576, then we will reject the null hypothesis. If the test statistic is not in the critical region, but in this region here between these two critical values, then we will fail to reject the null hypothesis. If you calculate 58 divided by 200, you'll get 0.29. The z statistic will be 0.29 minus 0.22, the null hypothesis proportion. And we use the null hypothesis proportions for what we put underneath the radical. 22% and 78% over 200, all under the square root. Don't forget to use an implied set of parentheses around the entire numerator. Divided by square root 0.22 times 0.78 divided by 200. The z-score that we get is 2.390. That doesn't fall in the critical region, and so we fail to reject the null hypothesis. That will be the conclusion of this test. The good news for you is that there is an even simpler way of conducting this test using your calculator. We'll go to Stat and then Calc. And this is a one proportion z-test. The null hypothesis proportion was 0.22. And we had 58 successes in 200 trials. The number of trials was 200. And this is a neither higher nor lower. And so we'll calculate. You can see then that the p-value is 0.0168. The z-score was 2.389. It follows then that we fail to reject the null hypothesis. What we end up with is a p-value of 0.016, I'll round it to 69, which is greater than 0.01, and so we fail to reject the null hypothesis. There is a third way of conducting these hypothesis tests called the confidence interval method. Really only suited for two-tailed test. Where you have the mean between some lower value and upper value. In this case, the proportion will be between some lower value and some upper value. You'll put alpha over 2 area on this tail and alpha over 2 area on this tail for alpha level of significance altogether. If the sample statistic falls outside of this interval, either to the left or to the right, then you reject the null hypothesis. If it falls within the confidence interval, then you fail to reject the null hypothesis. A New Jersey county clerk selected candidate positions on a ballot. In 40 out of 41 cases, the Democrat was listed first. The clerk was supposed to use an unbiased random selection method. Use alpha equals 0.05 to test the claim that the clerk was not biased in favor of Democrats. So here we have a particular proportion being the null hypothesis. The null hypothesis proportion should be 1 out of 2, assuming there are two parties, Republican and Democrat. So if the county administrator, county clerk were truly fair, the proportion should have been 0.5, but the alternative should be that the proportion in favor of Democrats is greater than 0.5. Since we're assuming the alternative is that the clerk is biased. We'll assume initially the clerk is not biased. The alternative will be the clerk is biased. We can use our one proportion z-test on our calculator. We'll press Stat and go to Tests. We'll do the one proportion z-test. The null hypothesis mean is 0.5. The sample, the number of successes was 40 out of 41. And The alternative hypothesis will be that the actual proportion is greater than 1/2, a one-tailed test. So we'll graph this and we'll see that the z statistic is over 6 standard deviations above the mean, which is very highly unusual. And the p-value is 5.6 times 10 to the negative 10. Something that's on the order of 10 to the negative 10 is really, really tiny. And so this is going to be so improbable that we will reject the null hypothesis. We will conclude then that the county clerk is in fact biased. The p-value really tells the tale. The p-value says 5.6 times 10 to the negative 10. If you move that decimal place 10 points to the left, you get 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros, and then your 5, 6. That's way less than 0.05. Therefore, we reject the null hypothesis. The county clerk was not using a fair, simple random process, and the county clerk was biased. Testing a claim about a mean is our next topic. In this case, we'll use a t-statistic. We'll use the sample mean minus the null hypothesis mean divided by the sample standard deviation over the square root of the sample size. This uses a t-statistic with the degrees of freedom equal to 1 less than the sample size. In our next example, elevator loading capacities are based on estimates of male weights, mean male weights. This mean has increased over the course of time. Use a random sample with n equals 40, a large sample, mean of 182.9 pounds, sample standard deviation of 40.8 pounds. To test the claim that the mean is 166.3 pounds versus the alternative hypothesis that the mean is greater than 166.3 pounds. So this will be a one-tailed test. Use a level of significance of 0.05. We'll press Stat and go to Tests. This will be a t-test. The mean, the null hypothesis mean, is 166.3. The sample mean was 182.9. And the sample standard deviation was 40.8. The sample size was 40. And in this case, it's a one-tailed test where the alternative hypothesis is that the weights have actually increased. You can see that our p-value is 0.007-ish, with the t-value at 2.57. 2.57 isn't bigger than 3, so we really do need to rely on the p-value in determining what's going on here. And since this is less then the level of significance of 5%, we will reject the null hypothesis. It seems that weights have increased, which is less than 0.05. That means we reject the null hypothesis. The null hypothesis is improbable. It's not probable that the mean weight really is 166.3 pounds anymore, that it has gone up and now is larger than 166.3. One could have done this the old-fashioned way with critical z-scores, putting 0.05 area in. Using our calculator to find the critical t-score, we do second distribution inverse t. The area we wish to use is 0.05. This actually will calculate the area from negative infinity up to 0.05, which will give us a negative value. If we want to get a positive value, we should use 0.95, leaving 5% on the right tail. The sample size was 40, so the degrees of freedom is 39. This will give us the critical t-score of 1.685, rounding it to 3 decimal places. 1.685. Our statistic, the z-statistic, is going to be 182.9 minus 166.3 divided by 40.8 over the square root of 40. Crunching those numbers on our calculator, we have left parenthesis, 182.9 minus 166.3, close parenthesis, divided by, open parenthesis, 40.8 divided by the square root of 40, close the square root, close the denominator, and we get a z-score of 2.573. Since this is beyond the critical z-score of 1.645, we reject the null hypothesis. The mean really isn't 166.3 anymore. It must be greater. We finally turn to testing claims about standard deviation. You'll recall that we had a chi-square statistic. We can use this chi-square statistic to test claims. We'll have a chi-squared left and a chi-squared right. We'll put alpha over 2 here, alpha over 2 here, and then whatever our chi-square is, we'll either fail to reject the null hypothesis or reject the null hypothesis, depending upon where that chi-square lands. Listed below are supermodel heights. In inches. Let's see, 70, 71, 69.25, 68.5, 69, 70, 71, 70, 70, and 69.5. It is claimed that supermodels have much less variation in height than in the general population. We'll use alpha equals 0.01 to test the claim that sigma is less than 2.6 inches. Here, the null hypothesis is that sigma is 2.6 inches, and the alternative hypothesis will be that sigma is less than 2.6 inches. To type in your list, you'll go to Stat and then Edit, and you'll see that I've already typed in the values here. Next, we'll go to Stat and Calc. We want the one variable statistics for the list that we just entered. And the value that we want is the sample standard deviation, which is 0.7997. That's the value that we want to use in testing this statistic. One, 2, 3, 4, 5, 6, 7, 8, 9, 10 values. It gives me an SX value, which is the sample standard deviation that I seek. It says it's 0.7997395409, some outlandish number. And we can use this number in our chi-square statistic. N minus 1 times this 0.7997 squared, I'll quit there, divided by 2.6 squared. This gives us a chi-square value of 9 times 0.7997 squared divided by 2.6 squared. 0.8514. That's our chi-square statistic. To finish our problem, we need to know the chi-square, the probability of getting a chi-square of this much or less. What's the probability of getting this or farther to the left? With the degrees of freedom equal to 9. We'll go to second distribution, and we'll go down to chi-square CDF. Chi-square CDF. The lower will be 0. The upper will be 0.8514, and the degrees of freedom will be 9. It's telling me that the area here is 2.90 times 10 to the negative 4. Moving the decimal place 4 points to the left, 1, 2, 3, 2, 9, we get a very small area indeed, certainly less than 0.01. Therefore, we reject the null hypothesis. That the standard deviation is 2.6 inches,